Okay, so last time we did section 4.4. Now we're into section 4.5. But before, just uh, one last thing from section 4.4. There's another reason why the zero matrix really makes sense to be called the zero matrix. So here's the fact. Uh, if 0 is a zero matrix and X is any other matrix, that it makes sense for you to multiply by, then 0 times X is equal to, 0. It might be a different sized zero matrix, but you get that. Or similarly, X times 0 is equal to 0. So let me just do a quick example to show what I mean. Let's take, say, the 2 by 2 zero matrix 0, 0, 0, 0, and multiply that against a 2 by 3 matrix 1, 2, 3, 4, 5, 6, and let's see what we get. What do we get? The first entry, the first row, first column, here's the first row, first column, 0 times 1 is 0, 0 times 4 is 0, so I get 0. First row, second column, 0 times 2 is 0, 0 times 5 is 0, I get 0. First column, third row, 0 times 3 is 0, 0 times 6 is 0, I get 0. The same thing happens on the bottom, and I get a different zero matrix. So it's not always the same zero matrix, but I get a zero matrix. Similarly, if I were to multiply, this will be an exercise for you. Try multiplying 1, 2, 1, 2, 3. That's supposed to be a 3. Let me just erase a little bit here. Try doing something like 1, 2, 3, 4, 5, 6. Again, multiply this by this matrix, which makes sense because this is 3 rows by 2 columns, and this is 2 by 2. Verify that this does indeed give you the 3 by 2 zero matrix. It should. Okay. So we'll get rid of that. And let's jump on to section 4.5, where we are talking about matrix inverses. And here we're talking about multiplicative inverses. So multiplicative inverses. Now we already talked about the identity matrix in a previous one, in one of the previous videos, but let's just remember the identity matrix is going to be a square matrix. It'll be an n by n matrix with ones along the main diagonal. And so, just the 2 by 2 identity matrix looks like this, and the 3 by 3 identity matrix looks like this. And more generally, you just keep putting ones down the diagonal, and everything else is going to be 0. Ones along the main diagonal, zeros everywhere else. I didn't write that, but let me write that. Zeros everywhere else. Okay. And what we saw was if I let I be an identity matrix and X to be any other matrix, where it makes sense to multiply I and x. I times x is equal to x, or x times I is equal to x. You know, that's what you expect the multiplicative identity to satisfy. Well, what is a multiplicative inverse in the case of, say, real numbers? Multiplicative inverse is somebody so that when you multiply, you know, a number by its inverse, you get 1. So a number x times x to the minus 1, that's how we typically write an inverse, is equal to 1. So 2 times 1/2 is equal to 1. 2/3 times 3/2 is equal to 1. -1 times -1 is equal to 1. You could even check that, say, the square root of 2 times the square root of 2 over 2 is equal to 1. So these are all examples of inverses, multiplicative inverses. And generally what we expect is the following. We expect that if A and B are multiplicative inverses, then basically A times B is 1, as is B times A. So it doesn't matter which way you multiply A and B or B and A, you get 1. Now the book goes through the logic here, but if we want if we do the same thing for matrices, well, what do we get? First of all, we want to replace the number 1 with our multiplicative identity, which is I, the identity matrix. But also, it turns out that if A times B is equal to B times A is equal to an identity matrix, that forces A and B have to be square matrices of the same size as the identity matrix that we are looking at. So let me just show a couple of examples of I guess inverse matrices. Let's look at, say, here's a simple one: 1, 2, 0, 1 times 1, -2, 0, 1. Let's see what they multiply out to be. The first row and column gives me 1 times 1 plus 2 times 0, that's 1. The first row and the second column give me 1 times -2 plus 2 times 1, that's 0. The second row and the first column give me 0 times 1 plus 1 times 0, that's 0. And the second row and the second column gives me 0 times -2 plus 1 times 1, and that is 1. So in that order, those two matrices multiply out to be the identity matrix. We also want to see that it goes the other direction too. Okay, so let's see it go the other direction then. So you write 1 minus 2, 0, 1 times 1, 2, 0, 1, and we'll multiply through. The first row, first column gives me 1 times 1 plus -2 times 0, that is 1. The first row, second column gives me 1 times 2 minus 2 times 1, that gives me 0. The second row times the first column gives me 0 times 1 plus 1 times 0, that's also 0. And the last one gives me 0 times 2 plus 1 times 1, which is just 1. Okay, so that checks out. Let's just do one more example. Let's do the following. Let's take, I don't know, I'm just coming up with something off the top of my head. 3, fifths, 4 fifths, negative 4 fifths, 3 fifths. Let me undo that. 3 fifths. I'm going to multiply that against its inverse. In this case happens to be 3 fifths, negative 4 fifths, negative 4 fifths, 4 fifths, and 3 fifths. And this multiplies out to 3 fifths times 3 fifths, it's 9 fifths, plus 4 fifths times 4 fifths is 16 fifths. Excuse me, you know what, this is a bad example to do. Why am I doing this example? Let me do this. Let me leave this as an exercise for you. So show that this is indeed equal to 1, 0, 0, 1, and go about and do it in the other direction. Great.